Good shape. All right, so this, all right, so there's a paper here. Oops, sorry. I don't think we need that. This thing might be useful. There. So, all right, so this paper, so there's this issue. If we studied coil collapse, the chain collapse, and you said like that's a lot like protein folding. So people want to use that as a model for it. But when proteins fold, they're inside of a cell, you know, and it's crowded with a lot of different molecules. So it's not in it. So the collapse that you looked at, like we were way over on the left side of the phase diagram, and it's in the ultimate dilute condition, right? And then you can cool it down there because there's a overlap concentration. The phase separates in this kind of region where just is a single molecule collapsing, right? So anyway, so that serving as a model for inside a cell, it's not exactly working because inside a cell, you're not in the dilute condition, you're in like a concentrated, semi-concentrated condition, right? So people want to model that. So in fact, like if you look, like I just looked for review articles in this molecular crowding, blah, 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 that kind of topic, like inside a cell, things are crowded, and you want to look at how the polymers, like the fundamental physics of how polymers act there. So anyway, this year, like this isn't even published yet, but basically there's like in 2024, there's like 4 major review articles in this subject, you know. So it's kind of like, so, and I'd imagine that last year there were 10, you know, so basically it is kind of an area that people are interested in for whatever reason. They, you know, essentially it's like NIH funding for people. Like if you're doing polymer physics, there's no money in it. But if NIH funding is like unlimited money, it's like people want to tie the things together to get money to do their whatever thing they want to do with it, especially computer simulations, whatever. Right. So anyway, so there's pictures of this thing here, just showing this kind of thing about stability, aggregation, like under different concentrations, right? So you can glance through this. I don't know how quickly you can glance. Basically, look at the pictures. Because when I say glance through it, you know, so it shows like the polymer is in the presence of some other thing. If the polymer is large or small, the things are large or small, then how does that affect how the chain behavior works, right? So this is more or less the motif of this paper that we're looking at. He goes through like some more, instead of cartoons, actual applications like a snail mucus or something, right? So basically, the never world of biopolymer stuff, right? So at some point you get to snail mucus. I don't know where it is at the end here. So that's kind of where these things all lead to. You know, there's the snail, or I guess it's a mussel, whatever, blue. Okay, so always these reviews. The guy wrote it. He's interested in mussels, you know, and then he gets this idea like the crowding thing is a popular topic. So then he writes a review, like say he wrote a proposal. So the beginning of the proposal has to be like a review of the stuff. So he already wrote the review. Then in the end of the proposal, it's about like, oh, we're going to study mussels, which had nothing really to do with the topic of crowding and biology. I mean, it has something to do with it loosely, you know. That's when you see a paper like this, that's generally the origin of it, you know? And it's easy to publish because you already wrote it. So instead of being a waste of time, you can publish the thing, you know, if the proposal doesn't get funded or something. So anyway, so that's kind of the ways things work. Anyway, this guy, I think, so this is a group from Spain. In some sense, it's an interesting paper in the context of that crowding. So again, like he starts out with 2 pages discussing this crowding issue in biology and how it changes the behavior of this coil collapse thing, right? And then he's going to study it. So he's got PMMA. So acrylate. So the acrylate group is here, the methyl acrylate has a methyl on it, and then methyl methacrylate's got another methyl here. That's plexiglass. That's like plastic windows, right? Or it's contact lenses are made of this stuff too, right? So anyway, so we got that molecule in here, and he's got this same acrylic group here with so the acrylic ether. So instead of it's got a ether bond here, and it's got some other acrylic groups out here, right? So it's something that's added on. He puts that in because he has this also acrylic-like cross-linking agent that has these vinyl groups on the end, and the vinyl groups can cross-link some part of the middle of this ether, like right here for some reason. I'm not sure why how that works. Basically, that hydrogen is apparently extractable, and this vinyl can open up, and you get ethyl group here connecting to this bond right here. So that thing that he adds is a cross-linkable group, so we can have these chains. It's the same thing. It's a single molecule nanoparticle. Right, same thing that we had in the other papers. You see that this is kind of a common theme now. Somebody started doing single particle nanoparticles, and they then jump on the bandwagon type thing. There isn't really any use for single particle nanoparticles, right? Basically, you can do it, and I think he's using a raft polymerization like we had in I think the first paper or something, right? So that's also a common theme. So this kind of controlled free radical polymerization. Anyway, so he's making these jello kind of, what do they call them? Boba balls or something for the tea thing? Is that what it is?
Boba balls.
Yeah, okay. But he's making boba balls. They stick it into basically milk because the milk's going to be like a protein solution. So it is like, it could be a biomimicry kind of thing if you want to look at it that way. I mean, I think he had this stuff made and then he went to this idea and he said, I'm going to do neutron scattering with it. Like one thing leads to another. And then, oh, this fits into this crowded environment behavior for polymers, which is like 4 reviews this year. It's like in 3 months, already 4 major reviews on it. So it's a hot topic, I guess, in that sense. And maybe he can get NIH funding or something, but he's in Spain, so he gets the Spanish whatever funding. In fact, it's always good to kind of look at the end and see like, where did the money come from that paid for this thing? So acknowledgement, so it's some kind of federal Spanish a way of making Europe. So he had some magic money that came in. And then technology and innovation, something program, whatever, Spanish. And then Department of Education. So he's got a variety of funding sources for this, none of which I know anything about, but basically none of it seems to be medical either. So in the US, this would be like, something would be like NIH on this, probably, but I think they're all in Spain. But ACS, the American Chemical Society, they decided like 2 years ago to put all the author information at the end of the paper instead of at the front, where you want to, like, usually you look at a paper, the title's interesting, who did it is like the next question. And like, is there anybody competent in this list? So this way of doing it is really awkward because it kind of makes it look like you're not interested in who wrote the paper, but anyway, so they're all Spanish somewhere in Spain. San Sebastian. I haven't been there, but Basque country. I've heard of that. So they're in the part of Spain that isn't really Spain, but they want to separate or whatever. Anyway, so he's going to use the like last time I talked about the Debye function. So he uses something more or less the Debye function, but not exactly, right? So he's got this kind of monster equation, right? So let me see if I can get the Debye function up here. He doesn't give it. So anyway, so he makes those materials. He's got variable molecular weights. So he can make these kind of solid ball things. You can make them small and large, and you can also make the matching chain small and large, just like whatever that figure 1 in this paper is. In other words, this isn't a new idea. Like, of course, he's doing this. So in other words, this is like the general thing that people are going to do. Right, so he's doing that, but he's making different chain lengths. He makes a large and a small one. He makes different ball sizes, large and small. So it's kind of just exactly what you would do if you were glancing at the most recent whatever review of the subject. And he's going to look at what happens to the size of the chain. So how does that impact how does that impact like coil collapse? Be the thing you want to look at. But what he sees instead is that the coils expand. When he puts the boba balls in, the milk expands. You really want to see it collapse, because then you'd say you're controlling protein folding in the process, but he sees expansion. So he just reports it. And I guess it's good enough that anyway, it's published, so it's good, I guess. But so anyway, so he uses this thing. So we have let's see. So I want to go back to the PowerPoint stuff. I guess that's no. I just want to get to that divide thing. Oh, here. The divide thing is in slides 2. I think it's 7. Let's pass that. There, this is a divide thing, right? So this is a Gaussian chain. And then Q is Q squared or G squared. And you have this kind of function, right? So, and then I went through, let me see. So if you take that, so you have a function like that, it's like indiscernible, like you can't make any sense of it at all, right? So what you want to see is Guinet's law, and you want to see a power law. So at low Q, you want to see Guinet's law. At high Q, you want to see a power law of 1 over Q squared for 2-dimensional, like dF is 2, right? So this capital Q isn't Q. And to make it more confusing, so this is how Debye did it. He used capital Q and small q's and normal Q. In this paper, he uses capital Q for small q. So it makes it a little confusing. And I don't have no idea why he used capital Q for small q, except that he doesn't exactly know, he doesn't really a scattering person. So he didn't know that was really a good thing to do, especially in the context of the Debye equation, which is generally written this way, right? So, right. So if you take for this equation, I think I did this last time, but if you say for low Q, so then at low Q, you can expand this exponential into this series. So exponential minus x is 1 minus x plus x squared over 2, because if you square a negative, it's positive. And then minus x cubed over 2 factorial, or 3 factorial, which is 6, right? And then it would be plus x to the 4 over 4 factorial, right? That's how you expand exponential. And at low Q, at low x, you usually take the first 2 terms, but for the Debye, you need to take the first 3 terms, because the lead terms in this are q minus 1, which would be 1 minus q. That cancels out, so you need another term, so this doesn't go to 0. So you have the q squared over 2. You take the next 2 terms, q squared over 2, q squared 3 over 6. Then you have a 2, so the 2 cancels out, and you have a q cubed over 3, right? And then you're dividing by q squared. So q squared, this goes to 1. So it becomes 1 minus q over 3. And then if you take the same trick backwards, you say 1 minus, then this becomes exponential minus q squared or g squared over 3, which is Guinet's law. So bingo, you have Guinet's law for the low Q extrapolation of this thing. Right? And at the high Q, you want the 1 over Q squared. And Q is large, and this exponential minus goes to 0. Like exponential minus of some big number just is 0, right? And then Q is large, you can forget about the 1, because Q is larger than 1. Q meaning Q, you're much bigger than RG for Q. And then your sizes are much larger than the coil size, because Q is 1 over size. So, and then basically you have Q over Q squared, which is 1 over Q, and Q is Q squared. So that gives you your power minus 2 for the Gaussian chain. All right, so you can get, so anything, you should be able to disassemble killer function into these 2 things, which have to be true, because everything, like I said before, everything is going to spin around. If you're taking a random orientation of any object, it's going to end up being like a Gaussian cloud. And the Fourier transform of that has to be Guenier's law. So everything, no matter what you're looking at, has to end in Guenier's law to the left-hand side of the scattering curve. And the high Q side has to either be Q to the -4 for a solid surface, or it has to be Q to the dimension of the thing, whatever it is. Q to the minus dimension, right? So basically, you're saying this is a Gaussian chain. Well, Gaussian chain is still going to obey Guenier's law, so I have to be able to get Guenier's law from it. I can. And then it has to obey this -2 law, and it can do that too. So because of that, this thing makes sense, right? The other thing to think about in this, I don't know if I have a plot here, but let me just go back to the all right, so in the homework, I'm asking you to do that for this weird function he has. All right, let me just go back here. Oh, all right, so back to here. All right, so there's another thing about scattering, or actually anything you do where you have a plot. Okay, so and you got to fit the stuff that you have to some function, right? So the first thing you really want to do, all right, so because this scattering is always going to be power laws, so you're going to do like a log-log plot. That's kind of the first thing you do with scattering in modern times. In the old times, you tried to linearize it, like the Zim equation, to try to make it into a linear plot, which also is a good thing to do. But basically, the log-log is the answer for scattering generally, right? So anyway, so you take the data, put it into log-log, then you look at the curve, and it's a featureless curve, right? So you'd say, like, how many things can you get from that featureless curve is like the first thing you should ask yourself before you start looking at equations. Because equations, this is a complicated system. Like you have two things, right? Actually, you have three things. You have the solvent, the polymer, and these gooey balls, right? So you have like three things in it. So in each of the things probably has like 4 or 5 parameters to talk about it. So you have, all of a sudden you have like 15 numbers that you could get, right? And you're sticking it into a neutron beam, and you get that data, featureless curve, right? So how many numbers can you actually get from this to talk about the thing if you know nothing about the thing, right? So anyway, so from this curve you can get 4 numbers, right? Because there's a straight line, that's 2 numbers. It's like a slope and an intercept, right? So you have like 2 numbers from this, and for a log-log, it's like the power and the prefactor. So Q to this something times Q to the something. So there's 2 numbers, the power and the prefactor. And then you have this flat number, so it goes to a flat number. You can get here another number. So that's 3 numbers you can get, right? And then that thing ends at some point, so that's 4 numbers. So there's 4 numbers you can get out of this curve, right? That's it. There's no other, yeah.
Is there like any relation between like that, which there could be like a linear region, like at a certain point? Is there anything you can get from that or not really? Like
You mean
like after it stops, that keeps going down
over here, where left or right?
On the right side.
Okay, so it goes down. You mean this is like tailing up a little bit?
No, like if it just keeps going down, could it be considered like a linear portion? So I know for like different.
Yeah, this is a line. This part is a straight line.
Yeah.
So that's 2 numbers. It's an intercept and a slope.
Is there something that you can get from that like portion from it, or is it just found between?
I mean, you can describe a line with a lot of different kind of intercepts if you want, you know, like when intensity goes to 0, there's an intercept there, right? So there's a lot of different, but it doesn't go to 0 in a log scale. Basically, you could make the scale log of whatever and make it go to 0. But it's just another way to say the intercept. There's only 2, you only need 2 numbers. How many numbers do you need to make a line? That's the question. So it's 2 numbers. It could be any 2 numbers, you know, it could be a lot of different 2 numbers, but basically there's only 2 numbers in that thing, right? It's a line. Yeah. So there's no more parameters you're going to get out of that except 2. They could be, so your interpretation of what those 2 things are could be vastly different, you know. In other words, if it's power 2, it could be a disk or it could be the spaghetti thing. So you could interpret it as spaghetti or as a disk, but there's only 2 numbers, just in terms of parameters, you know. So it's really important to be able to do this, because a lot of times you'll see a guy come over show a data set, it's a straight line, like a dielectric measurement on some material. Then you get the resistance, the capacitance, the 15 other parameters from a straight line. So you have to say, well, that's a lot of those parameters have to be redundant. So there's an advantage to that. Like if you have a theory like that, then you can start relating like why is it only two numbers you get out of it? Only two numbers are governing all these other 15 parameters. But basically there's two numbers there. So you have to there's a touch with reality here before you kind of get going. So the other two are like this thing goes to a flat number. That's a parameter, and there's like a place where that flat number ends. That's some other number. And you can fit that with a Gaussian. Again, so Gaussian is going to have a breadth and an amplitude. Yeah.
Looking at the Gaussian, it was one page backward.
In the paper over here.
Yeah.
Let's see, what happened to it? Wait a minute, no. Here. Yeah, this business, yeah. Yeah, sorry, it's.
So, what I was trying to figure out is how is this expressed in the chain in terms of working with the RNA and kind of how's it expressed in the chain, I guess, and like the application part for you to decipher exactly like what's going on with this equation.
Yeah, I mean, it's based on this idea that you have a random walk, right? So I did this with, so it's simpler to calculate the rate of gyration of a random chain. So you start saying, well, you define what the rate of gyration is. There's a center of mass, and there's every point along the chain, right? So the difference between every point along the chain and the rate and the center of mass squared divided by how many points that you took, like how many steps in the chain, that gives you this rate of gyration squared. And then you can reformulate that into this n minus m thing. So you know that the distance between one point and another in the chain is going to follow this NL squared thing. So you can plug that in. You can kind of rework that equation into this equation, n minus m, and then do some math tricks and end up with this equation that it's n squared over 6, right? So Debye did the same thing in this paper. You use that same RG approach to get that equation. So it's a little involved, like I didn't go through it. But basically, first off, he just says, in this paper, like, oh, it's going to be double sum, just like the rate of gyration. Then he just gives the answer to it. Like he just spits out the answer somewhere here. Just to the beginning. Somewhere at the bottom of one of these pages, it gives that answer. Here, right here. So that's that same equation, right? So then he says, like, how did I get that? And then he goes through like kind of those double sums end up being matrices, like when they're, so it's like it's n and m, the indices of the things. You have n at the top, n over here, and then he goes through matrix math to kind of solve it to get that. Yeah. Let's see if I can figure out how to zoom in here. Yeah, so basically, I'm not going to go through you can go through this if you want. The rate of gyration one's relatively easy to do compared to this one. And the rate of gyration one's kind of difficult to do. But if you want, you can definitely do it. Just it would take like 2 or 3 days to go through this thing. Basically, it's not the rate of gyration one you can do relatively quickly. And it's the same, it's kind of like the same it's the same motif to it. Like he's using the same tricks. At some point he uses that same, like this is the same, this is just the step length part, but then he goes to the same, using this same like let's see, using the same math thing about the power series. Like if you have a series of sums of the power, then you can get the what is that thing doing that? Yeah. If you have a upstairs, if you have a series that it's the sum of the powers of things ends up being this thing. This is just a math handbook thing. I mean, you can figure it out, but basically it's a math handbook trick. So he works this thing down. So he has the sum of the thing to the power one, sum of the thing to the power two. And he just uses this expansion to sub in for those, and he gets this thing. So he does exactly the same thing in the other paper, except it's an exponential to the IQ dot R, which makes it a little bit more messy to do. So but he ends up with the same equation. So he ends up with this Debye equation for a polymer coil that has, so you get that and you say like, well, can I believe him or not? Like, it kind of looks okay what he did. I can't really follow the math that great, but I kind of believe him because it's Debye. Then like, well, you want to check it. And the way to check it is, do you get Guinea's law at low Q? Do you get this power law at high Q? That's kind of how you need to look at it, because you don't have time to go through the entire thing. In this paper, it's even worse, right? So it's like this. So this guy ends up with this equation, which is going to, all right, so he says here, so nu is 1 over the fractal dimension, so 1/2 if it's Gaussian, or this allows for any dimension because these branched bubble balls are going to be like, have a higher dimension than 2 because they're branched. So df is the kind of the connectivity dimension, which goes from 1 to 3, depending on how branched it is. The higher number means higher branching. And then d min would be like the tortuosity of it, which would be 2. Right, so you have 2 times some number bigger than 1, you get a bigger df than if it's not branched. So anyway, nu is going to be smaller than 1/2 because its df is going to be larger than 2. So then you're going to have some other thing. So Debye's thing's based on 2. This thing allows you to go to different dimensions, right? So the origin of this equation, I mean, you don't really need to know the origin of the equation, but he gives this reference to Hamuda, who's a guy from NIST, and then this paper. So this paper doesn't help any. Like if you look at this paper, it doesn't help, right? So the actual reference for this is a paper that you can't get. I ordered it, so I'll scan it. I ordered the book, from the library, and I'll scan it. It should come in today or something. It's not. It's in the Southwest Reserve, whatever. So, which is this thing, Advances in Polymer Science, 1993. So this is actually a book. It's a book of the collection of different people contributed chapters. So he's got a chapter on like how to do this thing, right? But anyway, Hamuda is a guy. He's I think he's retired, but basically, or dead. But he's a Algerian, right? So the French colonized Algeria, and then they had kind of a Vietnam War in northern Africa in 1960s, right? And then French when they colonized the country, they made all the people in the country citizens of France, so they could just go to France. It's like Paris is full of Algerians, which is partly the problem. You see all the Muslim protests and stuff in Paris, and then the French are like those French Nazis kind of showing up to get rid of the people that they colonized and tortured. Basically they did a Vietnam on Algeria while we were busy doing other stuff. So no one in the US really remembers it, but anyway, so Hamoud is a product of that in a sense. He went to France. They worked with a guy named Benoit, who's like one of the most famous polymer guys. So he's got this chapter about this kind of how you deal with branching stuff, and it's 1993. But then Benoit did this in 53, right? And then again in 57. So Benoit is a great guy, a top guy. This one in French is actually the one that's, so French up until the 90s, they would publish some of their stuff in French because French is the best thing in the world. So this is Debye's equation here. And then he says something about in French about, oh, it doesn't work for branching things, so I'm going to fix that. Comes up with this integral equation with an exponential in it. So ends up with an integral equation that describes scattering from non-Gaussian chains. Right, this is a 57. There's another one in English. That kind of is the same subject. This is a Debye function. But he's using, there's capital Q, he puts in actually n u squared here, and u, I don't know, somehow it's the same function. And he shows the same kind of integral business going on here. So anyway, so he goes through branching here too. So this is 53, 57, he decides to publish the same thing in French, but except it's not summations, he does it with integrals, which is the final form of it. And Hamuda in 93, so 40 years later, publishes kind of the same thing over again in this other paper, in this book that I'm going to get a copy, and I'll scan it in and throw it in here. Anyway, so you end up with this kind of monster function here, wherever it is here. So there is kind of a story to everything though, like this, you know. So anyway, so Hamuda's at NIST, and he's like kind of pushing his stuff essentially, and the Spanish guys pick up on it. The Spanish guys did this work in Munich. There's a neutron scattering place in Munich. So somehow the Munich guys got the Hamuda thing, whatever happened, who knows. So they end up with this equation, which is basically the Benoit function, you know. So all right, so it's got, because it's not Gaussian, you don't get an analytic solution, you get this integral solution. So you have to have an integral involved in it. So he's got this fairly complicated function. So if you have nu is 1/2, then this thing will fall back to the Debye function somehow. So let's see. So gamma of 1/nu nu is df. So people are afraid to use the fractal dimension for some reason. So you use this new thing. Flory had the new thing. He didn't know what fractal dimension was. So the new thing's carried through since 50, whatever. And Flory had new. But anyway, it's gamma to the df. And then u is this capital Q thing, Q squared or G squared. He's calling small q big Q, which then he calls big Q u. It's just like wacky, right? So that tells you alone that the guy is messed up, you know. Anyway, so here this is capital Q, and this is df. Gamma is this integral, goes from A to B. So A is df and B is capital Q. So it's an integral to B being capital Q, which is the same. If you go back to the Benoit paper, it's exactly the same thing that he had. It's just rewritten in a more obtuse form, you know. So anyway, so and then this expression for U is also in the Benoit stuff, right? So these things already existed before the 93 Hamuda thing, so it's not even referenced to the right paper, right? So anyway, so that's okay though. So he has this function, and this function works pretty well. I mean, it works kind of within reason, you know. I mean, so within reason means you have to be able to get Guinier's law from this at low Q, and you have to be able to get the power law Q to the -1/nu, meaning 1 minus df at the high Q. So you have to do the same thing with this function that I did with the Debye function. And this is going to be a lot more paper to do it, right? But you can do it. You can do it though. I did it. So I think you can do it. So it's going to be like 3 or 4 pages of just keeping track of what thing is what, but then you can do it. So anyway, so that's possible to do. That's stage A of this paper. I mean, all right, it's only got stage A and B, right? Because the conclusion is not much, right? Anyway, so that said, so you can't just say like, I'm going to sum together the intensity of the Bobo balls, the polymer, and then he's also got this solvent thing floating around there. So he's got like 3 things in the system, right? No, if it's just the Bobo balls and the polymer, that's kind of the normal situation. You can use the RPA equation, which is 1 over the intensity is 1 over the intensity of the Bobo balls plus 1 over the intensity of the polymers, and then minus 2 chi. And the chi is like how the Bobo balls interact with the polymer. But if you put in a solvent in that also, there's a problem. Like if you have 2 things that don't mix, and then you want to mix them, then you put them in a mutual solvent. And then they both go into the mutual solvent, then they mix, and then you freeze dry it or something. Pull the solvent out quickly, and then you can get them stuck together. That's kind of a common way to do things. Right, so anyway, you can change the miscibility of two things if you put in a third thing that makes them miscible. I mean, it's kind of, I think maybe you would logically do that. Anyway, people do it, right? So that's kind of the situation here. All right, so if you look at it in terms of this, you have three chis. You have like chi between the bubble balls and the polymer, chi between the solvent and the polymer, and chi between the solvent and the bubble balls. So they're all like interfering with each other to get the things to mix. So it can be, it's a little bit more complicated situation than two things mixing, right? So, right, but keep in mind that the curve only gives you four numbers, right? So if you want three chis, you can't get it, like it's not there. Unless you do like three experiments where you change in neutrons, you put deuterium on the chains, and then you can contrast out and get different answers. So you could tag out the solvent, leave the two things together, hydrogenous. You could tag out one of the two things, leave the solvent and the other thing hydrogenous, or you could tag out the solvent and the polymer and leave the bubble ball hydrogenous. So you could do like 3 or 4 experiments. Then potentially, conceptually at least, you could get from those 3 experiments, you could conceptually get 12 numbers because you get 4 numbers for each of the 3 experiments. Theoretically, right? But actually the curves, anyway, whether or not you could actually do that is, who knows? But he doesn't do that. What he does is he takes a solvent and he matches it up with the polymer. So you can, because you can buy the linear polymer deuterated and you can buy the solvent deuterated. And his bubble balls he's making, so he can't really make them deuterated. You could, but it would be painful, right? So painful and expensive, right? So he's not going to make deuterated bubble balls. He could have done hydrogenous, he could have done 2 experiments and gotten 8 numbers, but he didn't do that. He just said, I'm going to do the easy one, which is like deuterated polymer, deuterated solvent, and hydrogenous bubble balls, right? So, and then he's going to try to ramrod that into this complicated RPA, which is also due to Hamuda, right? So this is also like a Hamuda thing. Like, how do you do RPA if it's 3 components instead of 2, right? So anyway, it turns out like, it looks like, right, first off, so he ends up with this equation, which is a crazy equation. It's insane. Like you can hardly figure out what's going on. Although I ask you to figure this out, okay? But basically, it's pretty hard to figure out like what is going on. First of all, the RPA should be like this inverse sum. Inverse of the intensity is inverse of the sum of the 2 intensities, and then plus 2 chi, this U thing, right? So U is going to be like 2 chi. Then when you have 3 components, he has this 1 over, so not means that just the single component alone, like in a dilute condition. But 3,3 is the solvent, so he's talking about a dilute solvent. Like, I don't even know what that is. Like S033 would be like a single solvent molecule floating around in space, right? And then the other ones are like a single, like you could put the polymer into the solvent, that would be S022, and there's S011. So you have these 3 things that are the dilute ones. So you have pure, one is like pure polymer, 2 is like pure, or 2 is, that's pure bubble ball, and then 3 is whatever a solvent molecule floating around in space, right? So he has those 3 components. Those are the 3 structures that would add together to be used in the RPA, which would normally be this relatively simple inverse sum. Suddenly, because you have these 3 chis also, then you have to account for all this stuff, you know? So somehow he doesn't explain how he does it, but he says like Hamuda did in this paper 25, which is the thing I'm getting. I'll get that and put it up so you can look at it if you want. Anyway, so then because he only has 4 numbers he can get, so he says like, someplace here he says, I'm going to get those 4 numbers. I wrote it down over here, but so he's going to say he's going to get RG1, RG2. He actually gets 5 numbers. So the 2 fractal dimensions, one for a bubble ball, one for non-bubble ball, one for the polymer. and then the two sizes of the things, bubble ball size and the other size, the chain size, and then the chi, which is just bubble ball polymer chi. And then he says like that chi changes when I put solvent in, which seems like a pretty reasonable thing to say. Like say it's just a different system. I'm just getting the mixing of those two things. I forget about the solvent. Right, so it's like a, yeah,
Are the components like 1122, are those like based on just Cartesian X, Y?
no, it means one mixed with one, like polymer. So one is polymer, two is bubble ball, three is solvent. So one means polymer, just, and if it's zero, it means dilute. It means it's in a solvent, it's dilute. It's just a structure, it's a scattering you would get from just the polymer alone, or just the bubble ball alone. If it's,
Just the diagonal.
I don't know why it's 1, 1. There is, is there any like 1, 2, S12 or? See that? Oh yeah, there's an S12 here, which is like used in this equation, right? To get the chi parameter essentially. So, all right, the other thing that's screwed up here, okay, is that, so this looks like a linear sum, but it isn't, because it's really like an inverse sum, because the S's, these aren't structure factors. These are just some function that he calls S. That makes it really confusing. Okay, so here when he says 1 over S, that's the structure factor. The form factor. That's the actual scattering from the polymer chain. Once he gets down here, he uses the same symbol. This is really 1 over the thing. Or anyway, this thing isn't the structure of the chain. It's not the scattering from the chain 1, 1. It's like, when it's 0, it's dilute, it's a single chain. This is the actual whatever. So this is a Hamuda thing. So it's pretty messed up, like kind of, but anyway, this is what we have. So the question is, does this make any sense? Right? So you want to say, if I put some conditions on this, can I get back to 1 over I is 1 over 1, 1 plus 1 over 2, 2 plus 2 chi. That's what you want to get. Like, does this equation give you that or not? Like it has to give the right answer to revert back to the thing you know, like the binary mixing thing, right? And in fact, when he does this thing, he says that under the assumption, so he says only under the assumption that chi 1, 2 is 0. So there's no mixing between the polymer and bubble ball. And then there's this 1, 2, and 2, 3. It's like a solvent. It's a single solvent with a polymer mixture chi parameter. Right. So he's going to make that assumption. So because he says that, then he can get, and then he also measures the bubble ball race gyration. He uses that. So he doesn't get 5 numbers, he gets 4. And the curve has 4 parameters in it. So it's possible to get 4 parameters. So I think he realized that. And then, so he fixes the RG2 to a dilute solution bubble ball that he has the number for. And then he gets these other numbers, right? And then basically he's going to get this chi number and say, like, how does adding the solvent, or how does the crowding affect the expansion of the chain and the interactions and things? Like it's something about the interactions and what the size. Size is RG, interactions is a chi, right? So, and he finds out that the chi goes to like immiscibility, so it drops to a low number. So high chi would be, let's see, chi is the attractive for the chain. So if chi is positive, it means it's phase separating. If chi is negative, it means it's miscible, right? So chi becomes more positive when he mixes the bubble balls with the polymer, meaning that it becomes smaller, meaning it gets more miscible, and then the size gets larger. So he kind of ends up with a conclusion that isn't protein folding, it's like protein expansion. You know, so it's kind of the opposite. The answer he gets is the opposite of what you'd want if you were looking at the Alfonso paper, where he's looking through that picture of the what you actually want to be looking at, this cartoon of the this business. But he does do like all these, does one this way, one that way. He has 4 options, like big balls, small chains, big chains, small balls, big balls. Right. So he does all 4 of those in this paper. But, so it's something to be said for it. But anyway, so what else? So yeah.
Next question. Chi 2 to, or 1 to 3.
Mm-hmm.
where it says that they would equal, is chi 1 to 3, is that? like-
Solvent, it's solvent, Bobo ball, and solvent polymer.
Okay, so,
Yeah, so it's as if you just had Bobo balls floating around and anyway, they're both they're both plexiglass, right? They're both PMMA with a little, one of them has a little bit of this cross-linking thing on it, which is also an acrylic. So it's kind of like he's saying, well, they would have the same chi with the solvent he's using, which is DMF, dimethylfuranide. It's kind of a nasty solvent. Like if you, that stuff, if like you spill some, like I had some and I put it on the counter and a screwdriver was there. The screwdriver just like disappeared, you know, like it dissolved. The metal part was still there, but the plastic part was gone. You know? So it's supposedly toxic too and stuff. Like Eero had his, I think he had his lab shut down for DMF. For some, it's like a toxic solvent, you know. But anyway, he uses it here. So anyway, so yeah, so so first, like look at the graphs, say like there's just 4 numbers, maybe say how you do that, you know. And then try to show how this works. When I did it, actually, I ended up needing to say that this thing was 0. When this thing is 0, so chi, there's an entropic part like the x ln x mixing entropy, right? And then there's this enthalpic part, which is chi. So actually, it isn't exactly when chi goes to 0, you get to the 0 entropy point. It's when chi equals that x ln x term, the entropy part, right? So this term in scattering nomenclature means that. It means when chi equals the entropy part, when they match up, then you have no enthalpic interaction in the system, and then that's kind of like the critical point, right? So I think when I did it, I had to say that to get it to work, to be the inverse sum. And it took 3 pages. You know, so it's kind of like messing. So first you write down, you have to write down all these definitions of what U are. Use this U thing, which is like kind of an energy of interaction, more or less. And then this thing all has the fingerprint of Hamuda on it, you know, which makes me kind of wonder. But so, and it doesn't, it kind of works, you know. So I'm still a little skeptical of it. I'll give you guys the original paper, the original book thing that he wrote about it, so you can kind of look at it if you want. But I think you can go through the math without doing that and kind of get to the conclusion that kind of get a shady feeling like it could be the right equation. You know, that Sue's
To be
using.
perfectly honest, I'm not sure if we.
All right, I mean, just try, you know. But basically you got to just write down these U things. Right? No, he says right up that these terms drop out, like the 1, 2 is 0. Yeah, and all the 1, 3 and the 1, 1, 2 and 1, 3s are equal to each other. There's just one chi in it. So these things clean up a little bit, right? And then don't use, just call this S330. Forget about the capital Q, because carrying that through just messes things up. And then the 0 is enough to tell you it's dilute. And then a lot of these terms, so there's terms that end up being once U22. So these things, this is the same expression as that expression. And then it turns out like that same expression ends up in here when you do this U12 squared, if you take this. So if you go through it, it becomes somewhat simpler after 2 pages. Things cancel out. So just look for things to cancel out, and then it becomes simpler. And eventually you'll get to the point where you're almost there, but if this thing was 0, you know, and he even mentions in the paper that's the critical point. He says that, but he doesn't say he actually used that to get it to work. But so anyway, whatever. Maybe there's some explanation for that, like why that has to be at the critical point for the thing to revert. At that point, you have no chi, it's just the sum of the inverse of the 2, 2 and the 1, 1, 2, 2 and the 2, 2 and the 1, 1 sum together to give you the 1 over the intensity thing.
you kind of just follow those equations through.
Yeah. This is a really good exercise. I mean, it's kind of like, seems like a waste of time, but like, you're going to see a lot of equations that you have no idea. So you have to have like some basis in reality that you can look at something like this. I'm pretty sure that no one's gone through this, you know, so it's basically like, what is your touch point in reality where you know it has to have this answer, right? So you find that point and you have a relatively simple solution to it. And does that thing give you that answer? Yes or no? If the answer is no, then the thing's bogus. The answer is yes, then maybe it's okay, at least you feel more comfortable with it. You may not be able to figure out where it came from, but at least it kind of acts, it acts like a dog. It might be a dog, but so something like that. So
Which equation are we trying to get back to?
the 1/, the equation you want to get is like this equation, like the 1/, the intensity, which is I. So it's going to be this IQ. 1/, that equals 1/S22 plus 1/S11. I mean, times, there's going to be a contrast factor, this delta rho squared. And then it should be plus 2 chi. It should be plus 2 chi on the other end of it. So that should be the answer for two things mixing. Two things that are like polymers that are intertwined with each other. So you can't say it's like that one plus that one, they're intertwined. So you need to use that rule. So I think you can do it. I mean, just try to do it. If you can't, just say like, I can't do it. But go like, at least try for like 10 minutes, like make some kind of reasonable effort at this thing. So then there's a couple of things about like, just look at this crowding thing, like conceptually, just look at the pictures. You can even Google it or something, maybe. There's like 4 review papers this year, so you don't have to use just the Alfonso, but and then there's something about his conclusion is that crowding reduces solubility. So explain why it might be the case. So this is kind of like just whatever you can say about that. Let's see. So his answer, I think, is that the thing increases in size and the solubility decreases when he adds the bubble balls. I think that's what he ends up getting. But so basically, if that is his answer, does that solve? In other words, if he has a problem, if there was a problem that he was dealing with in this, which is kind of outlined here, more or less like you want to study protein folding. So basically, protein starts out as a squiggly thing, and then somehow it's going to compact into an exact structure, like a key, exactly the shape of a key. It started out as like a giant spaghetti that's miles long, and then it collapses down into a key. So does this thing solve that problem or not? Or does it even get you on the pathway to get to the solving that problem? Or like DNA, the DNA molecule is going to be like meters long, and then it collapses down into a chromosome somehow. It's like, does this thing give you the answer to that? But again,
So that's where I was going to say, I'm a little bit more confused on that aspect of how the equation kind of move a little bit, because when you said earlier, when they drop in and expand, that means that it's unfolding and doing it without opposite of whatever.
yeah, that's the point. That's exactly the answer to whatever it's like, no, it's not answering anything. It's like kind of saying you can get the opposite of folding, That's not helping exactly, right? I mean, like, so someone did their PhD, they spent like 6 years doing this. They come out with the answer, oh, it didn't work. We still have to publish it, I guess. Maybe that might be it. But they still put it, at that point, you could change the framework. Instead of saying it's about protein folding, say it's about miscibilizing a polymer. And I mean, like add this stuff and make it more miscible. That could be another thing you might want to do. And then just get rid of the intro part and put it into like some kind of processing for cosmetics. I mean, then put a little review about that and say, oh, we figured out how to do it. Right. So, I mean, there might be a question to which this answers, but this isn't necessarily that, So, yeah, so that's kind of where this is going. Show that it reverts, and this is do that business that I did for the Dubai on this thing. And this is kind of like looking at this business, I mean, in the first step is to look at the plots and say like how many parameters. So he's got these equations with all these parameters in it. Can you actually do this thing? Like, and then he kind of goes in and says like, well, I'm gonna make these restrictions and I'm gonna measure this thing separately, and that allows me to do it, because then he ends up with 4 numbers he needs from the. The other thing is that so these are the slopes of the power law region, right? So they are on the top of each other, right? So can you actually resolve those two from a single power law? No, you're going to get one power law slope of minus 2.3. And then you're going to say, well, one of the things is a slope of minus 2, the other one is a slope of minus 5/3. And they sum up inversely to give you this minus 2.3. Like, is that really possible to do? Like, can you sum 2 power laws and get a third power law? I mean, can you actually do that, mathematically? I mean, I think maybe you could if you believe the RPA thing. So, but there's some question about, even though you have the right number of parameters in the data, if the parameter you're looking for is overlapped with the other one, like, can it actually be resolved, Like, so there's some question about, could he do that? He definitively comes back with those numbers in here someplace and shows, like, he discusses like different new values, right? It's for the, so new is 1/df. So these are the df values for the thing. So, so when this is small, it's a big df. It means it's branched. So, who knows? It's kind of to look at it and kind of weasel out what the truth is from this thing. Anyway, we're out of time, so hopefully that's okay. I can talk. I don't know if you want, but
I have a quick question.
Yeah.
The boba balls you're referring to, are those the single chain nanoparticles?
yeah. So, I mean, that kind of, to me, is what a Bobo ball looks like. I mean, in other words,
Okay.
starts with a linear chain, and then this group is going to cross-link. So the red things are the cross links, and then he ends up with this green Bobo ball, and then these other are the linear chains of the just PMMA, polymethyl methacrylate, plexiglass. Right. So, and those are just hanging around in the DMF.
Okay, thank you.
Right.